We're going to model with trig functions some more. In Buenos Aires, Argentina, average monthly temperature is highest in January, and that makes sense because it's south of the equator. And we're saying that it varies sinusoidally, or else we wouldn't be graphing these things. So we're going to make x equals 0 be January, which is, depending on the way that your brain works, kind of annoying because typically when we think of months, 1 is January, 2 is February, and so on. But in this problem, x equals 0 will be January, x equals 1 has to be February, x equals 2 has to be March, and so on. So when I'm asked about May, that's going to be x equals 4. Now we could do it differently, but we're just going to do it the way the problem tells us to. So in this case, I'm going to graph something. So I start at a high of 83 and I go to a low of 57. If I think about where that is, 83 minus 57 is 26. So that means my midline is going to be 13 away from each of these. So my midline is at 70. So that would be like the average temperature in the 3rd and the 9th month of this. So April and October, I think it would be. So I'm going to draw a cosine graph. And cosine makes sense in this case because x equals 0 is our peak, and July being our very bottom, it should make sense that we're doing cosine here. So this will represent 0, and it will repeat itself 12 months from now, probably because that's how many months are in a year. So we look at this and it's pretty clear what each of our tick marks is going to be just based on having an understanding of division, like 12 divided by 4 is 3. But if I want to write the equation, I need to do 2 pi over my period and realize that pi over 6 is going to be my b value. So now I'm going to write this function. The function will be y equals, my amplitude is 13, times cosine. B is pi over 6. I don't need any phase shift. And then I have a plus 70. I could write this in terms of sine or whatever as we did 2 days ago's video, but I'm just going to do it based on what the graph looks like. So that's a cosine graph. Then the average temperature in May, in order to do that, I have to sub in 4. So y equals 13 cosine of 4 pi over 6 plus 70. So I can do this with or without a calculator. Then let's just do it without a calculator and you can type it in. So y equals 13 times the cosine of, well, 4 pi over 6 is 2 pi over 3. And cosine of 2 pi over 3 ends up being negative 1/2 plus 70. So the cosine of 2 pi over 3 is negative 1/2. I actually didn't need a calculator anyway, because 70 minus 6.5 is going to be 63.5 degrees. So that ends up being my answer in this problem. Next problem, a tsunami, commonly known as a tidal wave. You can read all that for your edification. Water goes down from its normal level, then rises equidistant from its normal level up. So let's suppose that a tsunami with an amplitude of 10 meters approaches the pier in Honolulu where the normal depth of the water is 9 meters. Okay, so that would be 9 meters above sea level. So we would put a 9 here, 19 here, and negative 1 here. So is it possible for that to actually go below 0? Yes, it's very possible for the water to go below the typical sea level because the ground of the sea is a lot less than 0. So it's possible for the wave to go below what it would typically go. And we actually did a problem like that yesterday too. So the period is about 15 minutes. So I'm going to do 15 divided by 4 to figure out what I add every time. So my initial time is going to be 0. Then I have 3.75, 7.5, 11.25, and 15. And so it starts at its normal 9 meters, and then the tsunami hits and it goes down first, then it comes up. So that kind of looks like a sine graph. So if I write the equation of this sine graph, I get y equals -10. The 10 is the amplitude, times sine of, how do I figure out what b is? B is equal to 2 pi divided by the period. So 2 pi over 15 x, and then plus 9 because my vertical shift is 9. So I'll rewrite that down here a little bit so you can see it as we're doing the problems. Assuming that the depth of the water varies sinusoidally with time, predict the depth of the water at the following times. So at 2 minutes, we're going to sub in 2 for x. So that would be -10 times the sine of 4 pi 15ths plus 9. That's not something we know off the top of our head. So that basically means we are stuck a little bit. And so we have to type that in the calculator. So all 3 of these are just going to be calculator problems. I get 1.569 meters here. If I sub in 4, I would end up with 8 pi over 15 on the inside. That's -0.945 meters. And 12 minutes later, I would plug in 12 and I'd get 24 pi over 15. And that ends up being 18.511 meters. So you can just type those in the calculator, and that'll save you a little bit of, I'll save you time doing it, but in a calculator part of the test, you would have to actually do it on your own. According to your model, what will the minimum depth of the water be? And interpret this in the real world. So that would be -1 meters. And what that means is 1 meter below typical like ground level, or what would be considered like the sea level, or where the ground would meet the sea. But that's very possible because it's not like it's going beneath the ground of the sea. It's beneath the ground that approaches the sea. So it's really not unreasonable to think.